In this video, we are going to see how to verify the Gauss divergence theorem for the given vector. So the problem is verify Gauss divergence theorem for f is equal to x square minus yzi plus y square minus zxj plus z square minus xyk taken over the rectangular parallelepiped x bounded with 0 to a, y bounded between 0 to b, and z bounded between 0 to c. So, in this for the given rectangular parallelepiped, x and y are bounded with 0 to a, 0 to b, 0 to c. We have been asked to verify the Gauss divergence theorem. First, let us see what is Gauss divergence theorem. Gauss divergence theorem states that double integral f dot n cap ds is equal to triple integral del dot f dv. That is double integral of the vector dot product with the unit normal vector will be equal to the triple integral of divergence of that vector. So this is the equality given by Gauss divergence theorem. Verify means we have to check whether the double integral value and triple integral value, that is left hand side value and right hand side value, we are getting both same. That is what we are going to verify. So first we'll do for the right hand side volume, then we'll do for left hand side. Okay. So first we'll find the value of right hand side of Gauss divergence theorem, that is triple integral over the volume del dot f dv. This is what we are going to find first. So what is the given vector f in this problem? It is x square minus yz I plus y square minus zx j plus z square minus xy k. Generally, capital F is nothing but general form of capital F is f1i plus f2j plus f3k. Okay, here in this particular problem, f1, f2, f3 are given by the functions x square minus yz, y square minus zx, and z square minus xy. So for this f, first let us find del dot f, divergence f. What is del dot f? It is dou f1 by dou x plus dou f2 by dou y plus dou f3 by dou z. Okay, del dot f, del is an operator, I dou by dou x plus j dou by dou y plus k dou by dou z. F is a vector f1i plus f2j plus f3k. Then when you do the dot product, we'll end up with this. So here f1, f2 are specifically given. So let us find dou by dou x of what is f1? X square minus yz plus dou by dou y of f2, that is y square minus zx. Plus dou by dou z of f3, that is z square minus xy. So what is differentiation of x square minus yz with respect to x? It is 2x. When you differentiate y square minus zx with respect to y, it's simply 2y. Z and x are independent of y, so differentiation will become 0. Similar way, differentiation of z square is 2z. Differentiation of xy with respect to z is 0. So del dot f, we have got it as 2x plus 2y plus 2z. In other words, it can be written as 2 into 2 can be taken common, right? So 2 into x plus y plus z. So for this del dot f, let us find the triple integral value. So next one, we are going to evaluate what is triple integral del dot f dv. Del dot f is 2 can be taken out. So first let us write this one second. So this is right hand side, no? So triple integral, general form, first we'll write. Triple integral del dot f dv over the volume v. For this problem is nothing but triple integral del dot f, we have got it as 2 into x plus y plus z dx dy dz. But to solve the triple integral, generally the order we'll take is dz dy dx. So the inner limit is for the limit of z, middle is y, and outer is x. What is limit of z given? Z varies from 0 to c. Y varies from 0 to B. X varies from 0 to A, which is given in the question. We'll use that limit. Okay. First, we'll integrate this with respect to Z. So, 2 integral 0 to A, 0 to B. X, if you integrate with respect to Z, it is XZ. Y, integrating with respect to Z, YZ. Integration of Z is Z square by 2 between the limit 0 to C, then dy dx. Applying upper limit C on Y, on Z, and lower limit 0 on Z. So it is 0 to A, 0 to B, upper limit C. So Cx plus Cy on Z, okay? Cy plus C square by 2, lower limit 0 on Z. All the terms we have 0, Z, so everything becomes 0. So dy dx. Again, integrating with respect to y, it is twice 0 to a. Cx becomes cx y, integration with respect to y. Plus cy becomes cy square by 2 plus c square by 2. When you integrate with respect to y, it becomes c square by 2y. Between the limit 0 to b, and then we have to integrate with respect to x. Applying upper limit b on y. Upper limit b on y. So then this becomes 2 times integral 0 to a, upper limit b on y. So b c x plus b square by 2c plus c square by 2b. Lower limit 0 on y, all the terms we have y, so it becomes 0. Then we have to integrate with respect to x. 2 common. BCx. BC as such, integration of x is x square by 2. B square by 2. C, integration is x. C square by 2b, integration is x. Between the limit 0 to a. Apply upper limit a on x, lower limit 0 on x. So when we substitute upper limit a on x, this becomes 2 common. BCA square by 2 plus B square by 2CA plus C square by 2BA. Lower limit 0 on x, all the terms we have x, so becomes 0. So now all the terms we have by 2 common, so can be taken out. Then it is A square BC plus A B square C plus third term is ABC square. So 2 will get cancelled. So on all the terms we have ABC common. So if we take that out, then it is A plus B plus C. From the first term we have taken ABC, then we are left with A. Second term only B. Third term is C. Let us mark it as equation number 2. So the right hand side, triple integral over volume, we have got the value as ABC into A plus B plus C. Now we have to calculate the left hand side, that is double integral. That is double integral over, yes, the surface. What is there in the left hand side of Gauss divergence theorem? Left hand side is double integral over S f dot n cap ds. This is what we have to evaluate. What is the region of integration? It is given as rectangular parallelepiped. So rectangular parallelepiped. First let us draw this because it is double integration. So we have to get the surfaces. It's not like triple integral where at a stretch we can integrate with respect to the volume. So here it is double integration. So we have to split the surfaces. So xy is z axis. So let it be x axis. This is y axis. This one is z axis. So each surface is a rectangle. Okay. So let us mark the surfaces. Let it be A. This one B. The marking is our wish. A, B. We can mark with any alphabet. A, B, C, D. A, B, C, D, E, F. I just mark this with G, H. A, B, C, D, E, F, G, H. I give the marking for the edges so that I can take different surfaces. Okay, this is rectangular parallelepiped. So how many surfaces we'll have? Totally 6 surfaces. Okay, so for each 6 surfaces individually we have to calculate F dot n cap ds. Okay, surface 1, surface 2, like that we are going to discuss. Now, if suppose I take this surface, say that is B, F, G, and then C. This surface which lies on the x-axis, which passes through the x-axis, at what? So this is origin 0, 0, 0. This is extension of x-axis. So x-axis, what is the upper limit? X-axis varies from 0 to a. So this one will be x is equal to a. Okay, so in this surface, x takes the value a. Y and z varies. So x is equal to a is fixed for this surface. And what about ijk? Ijk are nothing but unit normal vectors passing through corresponding to the axis x, y and z respectively. That is, the axis x we have unit normal as I vector. Corresponding to axis y we have unit normal vector as j vector. And corresponding to the axis z, the unit normal vector is k vector. Outward drawn unit normal. So for this surface, from the surface, the unit normal should go out. That is the direction of unit normal. So for the surface BFGC, axis goes outwards. No, so the unit normal n cap for this surface is I. On the other hand, if we take the opposite of the surface, that is AEHD, this is the surface which passes through x is equal to 0. But what about the unit normal n cap? It should go out. Okay, so from this surface, it goes out means it will be of this direction. So x in the opposite direction. So corresponding n cap for this surface will be minus I vector. Got it? So for this surface, n cap is I vector. For the opposite surface, outward drawn is minus I vector. Correspondingly, for each surface, we can say. For example, if we take the surface ABCD, unit normal is J vector. Opposite to that, EFGH, unit normal is minus J vector. Got it? Similarly, we can say for other two sides also. This is how we are going to split the surfaces. We are going to have different, totally 6 surfaces. So 6 discussions we'll be doing and then we'll be integrating for each surfaces separately. So let us have a clear idea. Let us write for each surfaces separately what happens to F dot n cap ds. Okay. So first surface 1. So totally 6, no? Surface 2, surface 3. I'll mark it as S1, S2, S3, S4, S5, S6. I'll name it, name the specific surface name also. S1, I take it as the surface which is in x-axis. Okay, so what is the surface name? It is BFGC. BFGC AEHD. BFGC AEHD. Okay. So the surface name is BFGC AEHD. BFGC AEHD. The surface S3, I'll take the y-axis. The surface which is there in the y-axis. What is the surface in y-axis? ABCD. And passing through 0, y is equal to 0 is EFGH. Okay. And corresponding to z-axis, it is DCGH, DCGH, and lower part is ABFE, which is corresponding to the axis Z. Okay. So axis Y is ABCD. Corresponding to axis Y is surface S3, that is A, B, C, D. Next side is y is equal to 0. That is E, F, G, H. Corresponding to the axis Z, that is D, C, G, H, right? And Z is equal to 0. Passing through Z is equal to 0 is A, B, F. Okay. This marking is totally of our wish. Just to have a clear discussion, if we mark it, it will be easier for us. Okay. Next, n cap. What is the unit normal corresponding to the first surface BFGC? Just now we have discussed. Now it is I vector. The opposite side, it is minus I vector. The side which corresponding to y-axis, it is j vector. The opposite side, minus j vector. Corresponding to z-axis, n cap is k vector. Opposite side is minus k vector. Next, let us see what is constant. Which variable becomes constant for that particular surface. The surface S1 is passing through x is equal to a. Then that x is constant here. Okay, throughout the surface it passes through x is equal to a. So x is constant. X is equal to a. Y and z variables. Okay. The opposite side it passes through x is equal to 0. The y-axis, it passes through y is equal to b. Opposite side, y is equal to 0. Z-axis, z is equal to c. Opposite side, z is equal to 0. Then what is f dot n cap on this, on the each surface? On all 6 surfaces we have discussed. What happens to f dot n cap? What is f given in the question? F is given as the question x square minus yzi plus y square minus zxj plus z square minus xyk. Okay, when we substitute x is equal to a and f dot n cap means f dot n cap, which one we have got as n cap, only that coefficient will get value. N cap is I here, so f dot n cap will be x square minus yz. So in x square minus yz, we have to put x is equal to a. So which becomes a square minus yz. Okay, next f dot n cap is minus of x square minus yz. That if we put x is equal to 0, it becomes simply yz. Next, f dot n cap, that is j coefficient, y square minus zx, in which we have to put y is equal to b. So b square minus zx. Y is equal to, when n cap is minus j, it is minus of y square minus zx. Y is 0, minus of minus plus, simply zx. Now f dot n cap, where n cap is k, so coefficient of k, that is z square minus xy. When z is c, it is c square minus xy. When z is 0, it is minus of minus plus, simply you will get xy. What is ds here? Ds means the surface, what and all variable. So x is a constant here, so dx will become 0. So ds is simply dy dz. When x is 0, dx is 0, so dy dz. When y is constant, it is dx dz. Again, y is constant, so it is dx dz. When z is constant, the surface is dx dy. When z is constant, the surface is dx dy. Now the double integral is f dot n cap ds. For each surface becomes double integral a square minus yz dy dz. Limits of y 0 to b, limit of z 0 to c. For the second surface S2, it is double integral yz dy dz. Limits are 0 to c, 0 to b. For S3, it is double integral b square minus zx dx dz. Limit of x is 0 to a, dz is 0 to c. And for the next S4 surface, it is double integral zx dx dz 0 to a, 0 to c. For surface S5, it is double integral c square minus xy dx dy. Limits are 0 to a, 0 to b. The last sixth surface, it is double integral. Sixth surface, it is double integral xy dx dy. The limits are 0 to a, 0 to b. So now the left hand side of Gauss divergence, which is nothing but double integral. What is left hand side? Double integral f dot n cap ds over the surface S. Now it becomes double integral over S1 f dot n cap ds plus double integral over S2 f dot n cap ds, double integral over S3, S4, S5, S6. There are 6 surfaces. So calculation of double integral over S is nothing but calculating double integral of f dot n cap ds over all the 6 surfaces and adding all it together. So we will calculate one by one. So for the first surface, S1, double integral a square minus yz dy dz. The limit 0 to limit of y and z. Now already we have got this. Just integrating and substituting the limit. Okay. So the limits for y is 0 to b, 0 to b, 0 to c. So I'll do S1, S2, S3, S4, S5, S6 are similar. Okay, integration is similar. So this is a square integral 0 to c as such. With respect to y, if we integrate, it is a square y minus y square by 2 z. Between the limit 0 to b, and then we have to integrate with respect to z. Then applying upper limit b on y, it is a square b minus b square by 2 z. Lower limit 0 on y, all the terms we have y, so becomes 0. Then we have to integrate with respect to z. Then it is a square bz minus b square by 2. Integration of z is z square by 2 between the limit 0 to c. Upper limit c on z, so a square bc minus b square by 4 c square. Okay. So this is first one. Second surface is double integral over 0 to c, 0 to b. Function is, what is the function for S2 we have got? YZ dy dz. YZ dy dz. Okay. So which is simply YZ dy dz. So if we integrate YZ with respect to y, it is y square by 2z over the limit 0 to b, and then we have to integrate with respect to z. Then applying upper limit on y, that is b. So it becomes 0 to c, b square by 2, and lower limit z, and lower limit 0 on y becomes 0. Again integrating with respect to z, it is b square by 2, z integration is z square by 2 between the limit 0 to c. So it is simply b square c square by 4, lower limit becomes 0. So this is for second integral. Similarly, we can do the remaining surfaces S3, S4, S5, S6, and we'll end up with the similarity. That is, for the first surface, when we integrate with respect to yz, it is a square bc minus b square c square by 4. Similarly, second one, b square c square by 4. Third surface, if we do in the similar way, we'll get for third surface, the answer will be for S3. The answer will be dz dx, right? So b square ca minus a square by 4 c square. For S4 surface, it was b square c square by 4, no? So now it will be C square A square by 4. You can get similarity, okay? So S5 for surface S5, it will be C square BA minus A square B square by 4. For S6, it will be, what is S6? A square B square by 4. So LHS, we have to add up everything. That is A square BC minus B square C square by 4 plus B square C square by 4 plus B square CA minus A square C square by 4 plus A square C square by 4 C square BA minus A square B square by 4 and sixth surface, the double integral, excuse me, double integral value we have got it as A square B square by 4. The plus and minus signs of similar values will get cancelled. So we are end up with A square BC plus B square CA plus C square BC. So from this we can take ABC common. So it is simply A plus B plus C. Mark it as C. Now the right hand, mark it as 3. The right hand side of 2, that is triple integral over V, we have got the same answer. So left hand side and right hand side we have got the same value. So hence we have verified the Gauss divergence theorem. So this is the way to verify Gauss divergence theorem for any given three-dimensional space. Thank you.